Так. Так, вот это?
Сейчас.
Окей, хорошо. Так, значит, во-первых, у меня будет сегодня план немножко сказать про фактор по конечной группе, чтобы хотя бы примерно было ясно, как это происходит. Надо или не надо с явными формулками?
Давай.
Сейчас вы были в прошлый раз?
Нет.
Тогда давайте я это расскажу вкратце. Еще раз. А дальше план такой на сегодня глобальный. Доказать, что в торическом случае всегда есть разрешение особенностей. Вот. Я думаю, что при этом мы пойдем на английский, но пока то, что относится к прошлому разу, что мы не доделали. Давайте я быстренько напишу. То, что мы делали в прошлый раз. У нас было определение торического морфизма. Морфизм согласованный с отображением вееров. Каждый веер в своей решетке. Между решетками есть линейное отображение. Такое, что каждый конус целиком попадает в какой-то другой конус. Вот. И по факту самое ценное, что у нас там было, во-первых, было подразделение вееров. Мы просто берем, как бы каждый конус на какие-то конусы разбиваем и говорим, ну окей, тождественное отображение на решетках, и каждый конус попадает целиком в какой-то свой конус. Это первое. А второе, у нас был фактор по конечной группе. Ну, то есть не то, чтобы он был, мы про него сказали.
Типа точно касается ММ штрих, МПМ штрих фактор.
Ну, да. Когда у нас есть одна решетка, является подрешеткой другой конечного индекса. Тогда было сказано, что торическое многообразие одно и другое – это фактор по действительно фактору решеток, конечная группа получается. Давайте я напишу, что происходит в размерности 2. Вот если это к прошлому разу, размерность 2, пускай у нас есть, ну, мы хотим обсудить у сигма. Вот. Но несложно проверить, я не буду это проверять, но это можно сделать ручками, что любой конус сигма в каком-то базисе будет на самом деле конусом натянутым на D2 и некий вектор вида DF1 минус KF2. Где у нас K не превосходит, ну, то есть K от 0 до D минус 1. Вот, но здесь у нас по факту самое главное это D, которое является объемом фундаментального параллелограмма. Вот у сигма он двумерный, значит он порожден двумя векторами. Такая особенность в размерности 2. Соответственно, как бы да, если определитель 1, то мы просто можем загнать эти два вектора где 1, где 2. А если к какому-то числу, то будет вот так мы будем делать. Хорошо. И теперь, да, и, конечно же, поскольку этот вектор у нас должен быть примитивный, у нас они взаимно просты. Вот, хорошо. И тогда подтверждение, что формулками это можно записать так. Значит, я напишу, чтобы не напутать. Что у нас есть? Значит, у нас, очевидно, тут есть просто решетка, порожденная вот этими двумя векторами. Есть решетка, порожденная E1 и E2. Соответственно, у нас есть действие такое. Сейчас. У нас есть двойственные характеры M1 и M2. И, соответственно, so I'm just giving the explanation for the last lecture. If we are in dimension 2, how can we obtain any affine toric variety as a quotient of a direction of a finite group. So in dimension 2, we will have only cyclic singularities. If our cone is singular, then it can be proven that it is of this form, one primitive vector and the other primitive vector. And we want to give the action. So this is sigma. Maybe I should draw something like sigma check. It will be generated by this one. But it is in the reverse case. And
А у сигма это еще раз наше многообразие.
чего?
Напомните еще раз, что такое у сигма? Это многообразие, да?
Да, у сигма это
Спектр, понятно.
вот так вот. So what is sigma check in this case? This is sigma. This is d minus k.
Небольшое напоминание, мы спек считаем макс спекус.
Да. Сейчас, давайте сигма чек. Кто мне скажет, какой вектор будет ортогональным к этому? dk. No. This is kb. Okay? So these are generators of sigma check. And how many coordinates do we need here? I mean, how many generators do we need at to generate all the integer points of this intersection?
How many?
So at each level, we will take only one point.
Yeah.
So we will have d plus 1 generators. Okay? And what is the action? The action will be, so if we have monomials x and y, so monomials will be in x and y. Suppose that x will be mapped to so zeta will be the root, these roots of unity, and suppose that x will be mapped to zeta x and y will be mapped to zeta power k y. So it seems that this action will be indeed what we want to get, and the invariance of this action will be what we need. Okay? This is
Axi, what is this?
this is zeta. Is the these roots of unity.
С корни из единиц?
Yeah. So this is the finite group action such that its invariance will be the in other direction. Yeah, in this direction. Okay. So this is to refer for the previous time. Okay? And now, what are we going to do today? For those who came later, our aim for today is the Toric resolution of singularities. Okay. what is a smooth algebraic variety. Okay, so maybe I draw some picture. For example, just a very, very basic example to relate it with the usual sense. What is if I take such a variety, x equals y squared? Okay? How do we usually check smoothness? We take the tangent space and we look at its dimension. The dimension of t equal to the dimension of our variety. So, what is the easiest way to write the tangent space? We just differentiate this and we get okay? So at 0 it will be of dimension 2. Dimension 3, I mean. Okay? Any vector satisfies this condition at 0, 0, 0. So this variety is not smooth at the origin in any adequate definition of smoothness. Okay? So if we look at a curve, it is not smooth at the origin. Okay. Then, do you know that if we have the maximal ideal in our point x, ideal of all functions which vanish at x, then in fact this is isomorphic to mx quotiented by mx squared. Okay, did you see something like this? This is the tangent vectors modulo the functions which vanish in the second order. Okay, this will be more convenient for us. And so suppose that we have a defined Toric variety. So we take U sigma.
Что такое максимальный идеал в касательном пространстве?
Нет, он не в касательном пространстве. Ну, сейчас. Что такое касательное пространство многообразия в какой-то точке? Это как бы ростки функций. Вот. Что мы говорим? Ну, как бы вот. Ну вот, если у нас функция занулялась во втором порядке, то когда мы от нее дифференциал возьмем, она как бы тоже занулится в этой точке. Вы ряд Тейлора, когда пишете, многомерный, у вас просто останутся эти члены, и вы поставите эту точку, и будет 0. Ну, то есть это просто более удобное определение в касательном пространстве. Вот что мы здесь, по сути, сделали. В нуле зануляются x, y и z. А во втором порядке зануляются x квадрат, y квадрат, z квадрат. И вы просто говорите, окей, в этой точке вы отфакторизуете, один дело по-другому. У вас останется x, y и z здесь в факторе. Поэтому в окрестности этой точки x, y и z как бы все существуют, и поэтому здесь трехмерное касательное пространство. Ну да, это тяжело в первый раз, но в целом это очень стандартное как бы, определение. Не хотите, считайте просто дифференциалы, это будет примерно то же самое. Идейно это будет то же самое. Okay, so I wanted to say if U sigma is an affine Toric variety, let us denote by H is the set of minimal set of generators of the dual cone. Okay? It will always include all the edge generators and maybe some other points.
Intersections.
Yeah, definitely. Intersected with our lattice M. So the statement is that the dimension of the tangent space at this point at zero will be equal to the cardinality of this set. Okay? Why? If we have the 0 point, then it's ideal. Its ideal is so this is sigma check. We have some functions, some monomials in our variables. The maximal ideal of the 0 points contains all the monomials which are non-trivial. So M0, it is the set of all chi M. M is not equal to 0. Okay? If any variable comes, it will become 0. So, I want to use this definition. What is
Assume that 0 is inside our.
I wanted to say that sigma is a full dimension. Okay? It doesn't matter much, but to simplify the notation, I write that sigma is a full dimension. Okay? So,
But X is a U of sigma, right?
sorry? Yes, this is U sigma. Thank you very much. This is U sigma. U sigma. Okay, so I write the ideal of 0. And what is our algebra of regular functions? C U sigma is just a C of this. Okay? So what if I take M0 square? I will obtain only those points in our cone, which can be decomposed as M1 plus M2. Okay? So, almost by definition, the quotient M0 by M0 square is the set of where Mi is indecomposable. Okay? And so, its dimension will be equal to the cardinality of this set. Okay. Then, what about cones which are not a full dimension? if dimension sigma is less than dimension of our lattice, I just can say that U sigma is the product of the corresponding toric variety in span sigma and multiplied by some torus. There was some notation, but I don't remember it. Okay? And so, if we want to say whether it is smooth or not, this doesn't matter. The torus is always smooth. It only matters whether sigma is the corresponding variety is smooth in this lattice. Okay? And now I want to say something more exact. So, first lemma, which should be more or less obvious, if the set of ray generators of sigma is linearly dependent, so if we have more ray generators than the dimension, if our cone is not simplicial, so sigma is then your sigma is not smooth. Okay, is it obvious? Then I will write something. For example, if we have a cone with 4 generators in our 3-dimensional space. Okay? In this case, if sigma is not simplicial, then sigma prime is not simplicial. Okay? If, on the contrary, if sigma check is simplicial, then its dual will also be simplicial. Its faces will be the hyperplanes corresponding to the subsets of cardinality n-1. Так, краткий план. Я сказала, что такое гладкое многообразие, алгебраическое. Я сказала, что размер цветного пространства — это размер идеала по его квадрату. Ну, это вы знаете, да? Вот. И мы сказали, что афинное торическое будет гладким тогда, когда сигма чек порождается таким количеством векторов, как в размере. Хорошо. Okay. So if sigma is not simplicial, then sigma check is not simplicial, and then our set of generators of object contains all the ray generators. Okay, and it will be more than the dimension of our space. dimension. Stand sigma. Okay. So if a cone is not simplicial, then the corresponding affine toric variety is definitely not smooth. But this can appear only in dimension 3 or greater, because any cone in dimension 2, it will be simplicial. Okay.
Oh, it already has been.
Okay. Then the second statement. Maybe we need some word. A simplicial cone. A simplicial cone sigma is called smooth or regular. If the fundamental volume is equal to 1. If the determinant of, so let U1, Un be the rate generators of sigma. If the determinant of equals 1. And clearly, if sigma is smooth, if and only if a sigma check is smooth. So if our matrix has determinant 1, then, and if it is an integer matrix, then its inverse will also be an integer matrix. And it will give us the rate generators of sigma check.
Чего соответствует многообразию?
Пока, ну подождите, я пока сказала, что если конус как бы имеет фундаментальный определитель 1, то
Да-да-да. Ну,
двойственное тоже. Ну картиночки, когда рисуем картиночки.
я понял. А многообразие какое тогда будет?
Гладкое. Ну, в смысле, да, мы идем к гладкому
Сейчас
многообразию.
вы сказали, что если...
Я еще не сказала, я еще только собираюсь лему 2 написать.
А?
Я только лему 2 собираюсь написать. Еще раз, вот там написано определение гладкого конуса. Что вам не нравится? Вот смотрите.
Это вопрос
Вот давайте...
вперед, возможно, вы скажете.
Да, конечно, гладкий гладкому соответствует.
Ну, сейчас мы просто сказали, что если конус simplicial, то многообразие уже гладкое.
Нет, нет, наоборот. Если сигма не симплициальна, то оно не гладкое.
А если сигма симплициальна, то оно гладкое?
Нет.
Ладно.
Это же была картиночка,
Всё, я
смотрите. Вот есть был конус, вот было многообразие. Ну, примерно такой конус, я точно не знаю. Ну, вот,
Да, я понял.
все окей. So, if I draw a counterexample, so if so this is sigma with the fundamental volume equal to 2. So this is our fundamental volume. It is equal to 2. Okay? 1, 1 and 1 minus 1. And its dual will also have volume 2. So this is sigma, and this is sigma check. And what is the sense of the volume? If it has volume 2, then this parallelogram has a point inside or on its boundary. What is the volume for a simplicial cone? We take all its rate generators, 1, 1 and 1 minus 1 in this case. And we want to count the determinant. So doesn't matter, 1, 1 and 1 minus 1. it is minus 2. Its absolute value is 2. The absolute value of the determinant is equal to 2. So it means that by definition our cone is not smooth or not regular. In this particular case, the corresponding toric variety will not be smooth because we take sigma check. It has the same shape as sigma, and its fundamental volume is the same. It is equal to 2. And if it is equal to 2, there are some points inside the parallelogram or on the boundary. In dimension 2, it cannot be on the boundary. In dimension 3, it can be on the boundary. And now we see that H will contain 3 elements. In this particular case, with sigma generated by 1, 1 and 1 minus 1.
Okay, so you are claiming that whenever this thing, its volume is not 1, that is it is simply shear but not smooth, then this H will contain some points which are on the boundary of the parallelogram.
Inside the parallelogram or on the boundary, yes.
Inside the parallelogram, not necessarily on the boundary or on the boundary. Is it?
Let me write it down, okay? So this is the example which can be used to produce more examples. So lemma 2 says that let sigma be simplicial okay, then U sigma is smooth if and only if sigma is smooth in the sense of this definition. Okay. Let me first prove this direction. It is more difficult. Okay, this direction is more difficult. Suppose that U sigma is smooth, but sigma. Then suppose that U sigma is smooth, but the volume of U1 UM is greater than 1. Okay? Then we have a dual.
Date minus 1 will also do, right?
Let me. Okay, actually, it doesn't matter.
Okay. In the definition of smoothness, I think date plus minus 1 both are fine.
Okay, we can write plus minus 1. Yeah. Then we denote by M1, Mn be the generators of sigma check, and the volume or the determinant M1 Mn, its absolute value is greater than 1. So there exists a point from our lattice, an integer point, a point from M in the following figure. Lambda I M I 0 less or equal than lambda I less than 1. Okay? And all such points, the intersection of this object, this intersected with M, is the set H. in fact, H.
No, it's inside the parallelogram. We cannot guarantee that every time we will get the point on the boundary. It can be anywhere in the parallelogram.
I mean, sometimes it can be on the boundary.
Yes, sometimes, but we cannot guarantee it every time.
Yeah. If you take the product of this cone with the z-axis, then this point, which is now in the interior, it will become on the boundary. So this is peak formula, in fact. Формула пика. Встречали, да? Вот, по сути, она тут тоже, можно ее применить. Okay, so in this case, the cardinality of H will be clearly greater than N. And it will contradict with the fact that your sigma is smooth. And in the other direction, suppose that sigma is smooth, then after a change of base, after an integer change of base, and z being, yeah, change of coordinates. Sigma is just the curve generated by E1, En. Okay? And so sigma will be just the affine space. Вам понятно или не очень? Вы задавайте вопросы.
We cannot get extra Toric limit.
This is what I want to write down now. We can extract the torus if sigma is not a full dimension. I mean, right?
It's already simplified.
Okay. Maybe I should write down something else. I mean, if sigma is a full dimension,
Then it's just a affine space.
yes, this is just a affine space. If sigma is not a full dimension, then I should adjust the definition of what is a smooth cone. A smooth cone is a cone such that it is simplicial in the space it generates, and then its set of rate generators can be extended to a basis of the whole space. Maybe I will write down some statements which will be obvious for somebody and which will need some discussion at the seminar. So there are three equivalent statements. So we say that X is a torus, has a torus factor if and only if X is the product of X1 and the torus. Some torus. Okay? So there are three equivalent facts. First, our variety X has no torus factors.
What is it? X, what is it? Smooth manifold? What is it?
No, just X is a toric variety. not necessarily smooth, not necessarily affine. But in our lectures, we assume that it is normal. It is always normal. So X has no torus factors. And then the second, there are only the trivial morphism from our variety to C star. So all the morphisms from X to, no, not trivial, is only constant morphisms. So if we have a torus, then we have different characters. Characters, there are non-trivial characters which are not constant. And the third is that the rays of sigma generate the lattice n. If it is not obvious, we will show that 1 is equivalent to 2 and equivalent to 3. Okay? And also at the seminar.
X from sister is a group morphism of varieties, right?
No, this is a map of varieties. So X is a variety. We define what is a regular map, and the map which is given by some polynomials. So if it is given by polynomials and if it is not constant, then we will need to have a torus factor. So we cannot map C to C star regularly. So at the seminar, if U sigma is smooth, without assumptions on dimension of sigma, then U sigma is isomorphic to C power R times the C star power n minus R. More or less obvious. But if it is not obvious, this is a good point to stop and to think of it. Okay. And now, I think we can discuss singularities and the resolution of singularities. Any questions at this point? I didn't mention last time. If you know what is a proper map, in the topological sense, a proper map is a map such that the preimage of a compact is compact. There is an algebraic definition of properness which is more complicated, but the criterion, it is proved in the textbook, but the proof is quite difficult. I don't want to give it here. So suppose that we have a toric morphism. I recall that a toric morphism comes with a map of lattices. Phi is a linear map, so it is a group homomorphism. So we assume that since it is a toric morphism, it means that phi is so it respects, is compatible with our fence sigma prime and sigma. So each cone which is in sigma prime maps into a cone of sigma. So the criterion. So this map, I write phi x. Phi x is proper if and only if phi minus 1 of sigma equals sigma prime. Okay? So it is defined on the lattices. So this object is some subset of this lattice. We ask it to coincide with sigma prime. And also I don't want to define it, but to be a projective morphism, we need it to be a proper morphism. So I don't want to go into these details today. Today's proof will be difficult, but in the combinatorial sense. And we will prove the existence of the resolution of singularities in a way which can be said this map is also projective. But we will not discuss it today. So what are the singular points of an arbitrary Toric variety? And how can we construct the resolution? So we take a Toric variety X sigma. Some of its cones will be smooth and some not. I didn't mention that if sigma is smooth and tau is a face of sigma, then tau is also smooth. Okay? Do you believe? We can choose a basis. So first of all, if sigma is simplicial, then each face is also simplicial. And then we first choose the basis in tau, and then extend the basis of sigma. If you find the area of a parallelepiped, its base and its height. If the base has the area greater than 1, then all in total, the height will be integer and the area will be greater than 1. Okay? Понятно примерно? Хорошо. Now the fact which follows from the orbit-cone correspondence, if we take the union over all cones from sigma such that they are smooth over the affine open subsets U sigma, it will be the smooth points of our variety X. And the set of singular points it is denoted usually by X sim. It will be the union of a sigma is not smooth. O sigma bar. closure of the corresponding torus orbit. So we see that for each fact, so sigma 0 is the set of cones of all cones of dimension 0 which are in our fab. It is the origin. The origin is always smooth. And U0 includes U0, which is the torus. Okay? And for each UI is an element the notation sigma 1 is the one-dimensional cones of our fan sigma, so array of some cone. We always have so each one-dimensional cone is automatically smooth, and so we will no, it's not a good way to say this, but we will have some codimension 1 subvarieties here, which will be also smooth, which are not in our torus. I don't want to write it down right now, but I want to say that not smooth cones will be in dimension 2 or greater, and so the codimension of X singular it at least 2. It agrees with what we know. So we always have enough smooth points in our variety X. So, do you believe in this fact?
Doesn't this imply X is always normal?
If X is constructed via Fn, then it is always normal.
Okay, yes.
So today we deal only with normal varieties. But I just wanted to draw something which relates you to facts we know from algebraic geometry. In this fact, you can prove by hand that if you take a point which is not smooth, then it corresponds to a non-smooth cone sigma multiplied by some torus. And also, if you decompose this into orbits, you obtain only the orbits which contain sigma. Tau, such that tau contains sigma, and if sigma is not smooth, then a bigger cone is not smooth neither. And then it will indeed be non-smooth. So just to explain this, you need the orbit cone correspondence, and all this stuff we have done before in this lecture.
То есть вот такие орбиты состоят из точек из сингулярности, да?
Да. So I mentioned that in one torus orbit, either all the points are smooth or all the points are singular. And do you remember, if sigma is not of full dimension, we can say that O sigma contains a torus and some torus orbit in the space of its dimension. So in fact we discuss only the singular points in maximal dimension. Okay, now I want to define what is a resolution of singularities. If I forget something, please correct me. So resolution of singularities. So we assume that X has some singularities. we want some map from x prime to x, f such that f proper, such that x prime is smooth, and if we take phi minus 1 from the smooth points of x, is mapped by phi, no, not phi, f here and f here, f to it should be an isomorphism. Okay? So you have some x. For example, it is a cone. It has one singular point. You want to take something which has not exactly this, but you change this singular point by something. This is not a good picture. Maybe something like this, and something instead of this point. So it will be isomorphism on these parts, and it will map something smooth into our bad point. Is it all? Okay, it seems that this is all, and the advantage is that it is by this it will be birational. So we want to find something smooth which will be birational to our initial variety. So a resolution of singularities exists for any algebraic variety, but this is a hard statement, and the advantage of toric varieties is that if we have a toric variety x which is not smooth, then we can precisely give this toric variety x prime and explain what is the map f which will give us the resolution of singularities. And now we have lots of combinatorics. С этим все понятно? Если не нравится, спрашивайте. Okay. Now, what are we going to do? I didn't mention today, but if we have a fan and if we subdivide it, so if we have sigma prime is a subdivision of our fan sigma, then we have the map phi, which is identity on the lattice. It respects our fans. It sigma prime and sigma, and also it is proper because phi minus 1 of our fan is our fan. So if we have a subdivision, it is a very good candidate to be a good toric map. Now we want to define what is a star subdivision. So there are different star subdivisions. The most basic star subdivision was when we did a blow up. So if we have a sigma, which is just the octant, the star subdivision of such a cone sigma is that we add one ray, which is the sum, and we say that this is a blow up of C2 at the origin. This was basic, but we will use a more complicated subdivision. So this is star along sigma. And now let us along use star subdivision along some vector mu, which is in the support of our fan sigma. It will be a little bit more complicated. So, first of all, if a cone sigma doesn't touch, if mu doesn't touch sigma, then sigma will remain unchanged. So, how do we define it? If u, then sigma is in. So our sigma prime is a star subdivision along sigma. Then we include sigma prime. Then we include sigma in our new fan sigma prime. Okay. Then suppose that.
What name is it called?
Sorry.
What is name? A point, a cone.
This is. It is a point in our fan, but in fact this is a ray. Not much difference if we take an integer point in sigma or we take a ray. So maybe I should draw an example. Suppose that we have a cone with 4 generators in our 3-dimensional space. Okay? So these are 4 generators. 1, 2, 3, and 4. Okay? My aim is not to change the race of our fan. I will say in a few minutes. So if I want to get a resolution of singularities, and if I want x prime to have the same set of smooth points, I wanted to remain the rays intact. Toric. I need sigma prime of 1 be sigma of 1. Okay? I want it to be isomorphism at the set of smooth points. So if I add a ray, I will add smooth points. I don't want it. So now I want to take, for example, mu here. This will be mu. Okay? For example, this face of dimension 2 doesn't contain mu. It will remain in our fan. And now we add cone nu tau, where nu is not in tau, and the cone generated by them nu tau is in some sigma which is in the initial fan. Okay? In our picture, for example, this ray and this tau generate us the initial phase. Now this ray and this ray will in fact split us the cone into two parts. So we add in this square we add the diagonal. So we add this diagonal, and we add a two-dimensional phase which passes through this diagonal and nu. Okay? In fact, for this cone and this nu, the only thing which changes is that we add this plane which cuts our solid cone into two halves. So this is the definition of the star subdivision along sigma.
This is cone of sigma and tau, right? And the last.
This is the cone generated by our new vector and our old cone. This is tau. This is tau. This is tau. In some sigma inside our initial fan. So the old star subdivision was in fact along this nu. Okay?
Nu was not a ray of the cone.
In this definition, it doesn't matter whether it is a ray or not. Even you can take a 0, but nothing will change. In fact, this definition works for any tau or for any nu which is in the support of our fan. So we need to prove that it is a fan. Maybe if somebody has to go to some other class, first I prove that there exists a Toric resolution of singularities, and then I will show that the star subdivision indeed gives a fan. It is a fan. Okay. Let us use this fact and let us prove that we have for any fan sigma we can construct a toric resolution of singularities. Okay? So we suppose that we have some fan sigma which can contain simplicial cones, and it can contain cones which are not simplicial. So now fix sigma construct sigma prime. So we want if sigma is not simplicial, Okay, first case if we have some cones which are not simplicial. So lemma is there exists a sequence of star subdivisions for u in this set, making a sigma simplicial. Okay? How does it work? At the level of idea, if we have a cone which is not simplicial, then we want to triangulate it by place going from one vertex. And it will give us the required. More formally, let me make some maybe induction on dimension of sigma. So I equals 1, all cones from sigma 1, etc. sigma I are simplicial. Okay? Because any cone of sigma 1 is simplicial. And then this step take a fan sigma such that all comes from sigma 1, sigma I are simplicial, and sigma from of dimension I plus 1 is not simplicial. But so we have some finite number of such cones. If we take any of these cones and we make a star subdivision along one its ray, right, over such sigma, of any of such sigma, okay? Then what happens if we take mu, and if we know that all, so in this case we have a cone of dimension 3 which is not simplicial, but all the cones of dimension 2 are simplicial. Okay? Then when we make a star subdivision, the cones which change, they will become simplicial. If this object is simplicial, it has I generators and it has dimension I. We add one more generator and one more dimension. We receive this. So it will be of dimension I plus 1 and it will have I plus 1 generator. So all the new cones will be simplicial. So the non-simplicial cones of dimension I plus 1 will be here and their number will reduce. I mean, if we have a fan which has two cones of which are not simplicial, which are of dimension 3. For example, I can't draw, but if they touch by this face, if we can start with this star subdivision, we'll subdivide this one, and then we will take another one, we will subdivide the second one. For example, it could happen that we started with their common ray, then one operation will be enough. But we don't worry, we just take any ray, we make our procedure, and the number of bad cones in this fixed dimension will decrease. And so this process will stop. Okay? So star along star sigma along this mu will have less non-simplicial cones of dimension I plus 1. So we make all the cones of dimension I plus 1 simplicial, and then we pass the cones of dimension I plus 2, and so on and so on and so on. So I repeat that at each step, we do not break the condition that all the smaller cones are simplicial. So if we make any star subdivision, if we know that all the smaller cones are simplicial, then the new ones will be also simplicial. Okay. So we are done with this proof. We've done the induction. It needs a finite number of steps. Okay. Now we have a new fan which has the same set of rays. We didn't change the rays. And now we can assume that our fan is simplicial. Okay. If all its cones are smooth, then we are done. What if not? If there exists a sigma in sigma which is not smooth, then we want to make the procedure similar to what we had at the beginning of the lecture. So it is not smooth, but it is simplicial. It has so if all the cones of maximum dimension are smooth, then all the cones are smooth. Now, if all the maximal with respect to inclusion cones are smooth, then all is smooth. So now we will use some descent. Suppose that we have a cone which is not smooth. It has generators U1, etc., UN. Such that the determinant U1, UN is greater than 1. Okay. Then we want to seek for a point in this figure. So take a point. No, not in sigma, in sigma duo. So in sigma duo, no, not in sigma duo, in sigma. We have a point in the lambda plus lambda and UN. distinguishes in our lattice and with this condition. With the condition less than okay. This is our figure. If the determinant is greater than 1, then we have an integer point here. Suppose that u is here. Then the statement is that it could happen that some, so we will take mu equal to this point u. We want to make star mu, and we say that the number of fundamental parallelepipeda with the same volume will decrease. Okay? Maybe I should draw the same picture. What is our picture? 1, 1, 1 minus 1, which has the center. Okay? If it is in dimension 3, it is so this is 0, u1, u2, u3. We take this point which is at the boundary, and we will make this star subdivision along this point. So how can we explain that the number of parallelepipeda with the same volume will decrease? So we had a cone generated by this one, and now we will have n cones generated by u1. We skip ui, un, and u. Okay? What will be the volume? Volume of such stuff without ui, but with u, will be lambda I. Okay? Just because when we calculate the determinant, if we have such a point, this and this doesn't matter. Only lambda I ui will matter. It will lambda I times the initial volume u1, etc., un. Okay? So all the obtained volumes, if they are non-zero, they will be less than this one. Okay? If we have the cones of the same dimension and with the same volume, we will now work with them, and so on. So we will diminish this volume in this dimension, and at some step this process will stop. How should we act? If all the maximal with respect to inclusion cones now are splitted, then all their faces are also smooth. So this process will stop. Okay, we are almost done. So I have proved that there is a Toric resolution of singularities. It is obtained by a sequence of star subdivisions. And so, if you are interested in it, this is a proper map, and this moreover is a projected map. We are cannot prove it right now. So I have proved that there is a Toric resolution of singularities. If you have to go, or you can go. If not, I will go back and show that the stress and the subdivision is indeed a fact. Okay? Let us show that it is indeed a fact. What was our statement? Stress subdivision. What is the definition of a fact? It is a set of cones such that each face of a cone is also in our list, and the intersection of two cones will be also a face. And also we want to show that it is a refinement of the initial fan. We also will need. Okay, so the faces of all the cones. In the first case, A. In this case, are already in our fan because they do not contain new, they didn't change. Faces of B. So it will be the cones of U and faces of tau. Either it will be faces of tau or cone of U, mu, where mu is a face of tau. Okay, then
sigma is not contained in U.
yes, and sigma nu is not in U. Clearly, yes. Then intersection of cones. A intersected with A is okay because as before they are in our fan and they do not contain U. Then intersection of some old sigma and some this stuff, it will since A and B, a face of this kind and a face of this kind. Since nu is not in sigma, it will be tau intersected with sigma, which is in the initial fan. Okay, and now if the intersection of B and B, one cone of this kind and the other cone of this kind, it will clearly be the cone generated by our nu vector and tau 1 intersected with tau 2, if we define them tau 1 and tau 2. Okay, this is easy. And now if we want to show that in fact the cones of the B kind split sigma, it is a little bit more complicated. I need some space to write it down. So sigma is the union of all cones obtained in B of type B. So I will, I can do it like this. So how can we prove this? Suppose that mu belongs to sigma. If you want, you can take the minimal sigma, such a sigma that mu is in its relative interior, but this is not necessary. So let M1, Mn be the ray generators
Now we are proving that they have the same support.
Yes. Of sigma check. So at this step, it was the very beginning. We had no assumption whether it is simplicial or not. Just an arbitrary cone sigma such that mu is in sigma. It is in sigma. And I repeat, it is enough to show this for the minimal sigma. So there is some minimal sigma, a cone such that mu is in its relative interior. So if we take sigma and mu is on its boundary, then the boundary is the union of the faces, and we can take a face. And so if we show that this particular sigma, for example, as that picture, where is the picture? In this picture, we show that this down face is the union. Then for the cones of greater dimension, it will be also true. I mean, we show that the support is the same. I mean, we will show that here the support is the same. And more or less automatically, the support will be the same for the bigger cones, since they were obtained as the cone over this nu and something else. Okay. Okay, so we pass to sigma du. We take its ray generators and we know that the scalar product of mu and of mi is non-zero, is non-negative for all I. Okay? This is just by the definition of what is a sigma check. And we can find the minimum. Let us define lambda is the minimum for all the non-zero scalar products when mu mi is non-zero. Mu mi divided, sorry, one moment. Yeah, I'm sorry. So, what is the picture? We've had our cone sigma. We've had some nu here. And let us take u in sigma. We want to show that u is in some part of sigma now. Okay, so this is our U. We want to find the new cone in which new cone is U. Okay? And let us take lambda, the minimum of all UMI divided by UMI. Okay? So we want to show that, so this is some MI, which will give us some phase of sigma. So in some sense, we say that now this vector U will be in the cone generated by the corresponding, not here. So I equals 0. This is a phase. We will show that U will be in the cone generated by U and that phase of sigma. Okay?
Can you repeat the last sentence?
Yes, this is the idea. The last sentence was the idea. So we have our cone sigma, and we have our vector U along which we make this class of division. And now we want to show that the support of the two fans is the same. What does it mean? So
We take a U.
U from the old fan, we want to find a cone in the new fan in which it belongs. So, in some sense, this is the choice of some generator of sigma dual. A generator of sigma dual will give us a phase of sigma at the level of idea. It will be the phase with which we can take the cone U and this phase, such that U will be in this cone. Okay? So in dimension 2, what happens? This was sigma, this was our U. So now we had one cone, we have two cones. We take U, we want to determine, so we want to prove that it belongs to one of these two cones. So maybe it is intuitively clear, but I want to give an accurate proof. Okay. So this is the choice of I.
А мы же не хотели лучи добавлять, или нет? Или мы? Вот сам.
Ну как вам сказать, да, просто на такой картинке это самое. Мы не хотели добавлять лучи, не обязательно это... Ну, в доказательстве все хорошо. Картинка просто не может... Я не могу нарисовать картинку с тем же лучом, чтобы она была интуитивно понятная. Опять придется рисовать четырехмерный конус с тем же лучом. Ну вот у меня тут написано, что, еще раз, я беру только те штучки, где не 0. То есть таких будет немного на самом деле. Если она луч, таких будет сильно не все. Ну еще я сказала, что вот мы берем то, в относительной внутренности которого оно лежит. Если мы покажем, что оно разбивается, то все разбивается тоже. Okay. Can I continue? This is just a formal notation. We have chosen some mi and we have chosen some lambda. Okay. We started with u. The statement is that if we take u0, we define u0 as u minus lambda mu. U0 belongs to sigma. Let us explain it. So sigma is given by the equations. The scalar product with all and I is non-negative. For any J, if you want to write it J. What is U0MJ? Okay? This is UMJ minus lambda UMJ. So we're interested only with those indices. So we can write down. There are some indices when this is a 0, I such that UMI is 0. So this will not matter. This will be non-negative. 0 M. No, this is. Oh, one moment. So there are two cases. If this is 0, it is not interesting. Okay? I want to show that this scalar product is non-negative. So, if this is 0, it is clearly non-negative.
But it will be 0 for some J.
Yes, that's okay. It is non-negative when UMJ is 0, okay? Since this is non-negative. And if UMJ is non-negative, we can rewrite it. It is UMJ times UMJ over UMJ minus lambda. So since lambda is the minimum, it will also be non-negative. Okay? So we have shown that this vector is still in sigma. And now we can now let us fix any I with this equality. So now we fix I such that this is minimal. There is a phase. There is a phase mi equals 0 of our sigma. So tau will be a sigma intersected with mi equals 0. Okay? And in fact, U0, as you have noticed, it is It is in this phase tau. Okay.
What is it? Is MI?
Is minimal. I write that it is the index where we obtain this minimal value.
And when you are intersecting it with that MI, what is the index of index?
Mi. This is I. This is I. I. Okay. So Mi is in the dual code. So this is an equation on overcome sigma. Since Mi is the generator of sigma check, it is indeed a phase. Tau is a phase of sigma. So we have shown that this U0 is in this phase. And in fact, we can decompose U as U0 plus lambda U. It shows us that U is in cone generated by mu and tau. And we have shown that these two fans have the same support. Okay, I think that's all for today. Any questions? Вопросы? Так, one important, maybe two important things. First, there will be no lecture next week. And no lecture at the... За счет недели лекции не будет. Сейчас, подождите, я раздам листочек, но не сейчас, я, наверное, сейчас скину. Дедлайн мы придумаем, вот, вы решаете листочек. Что еще надо сказать? Вроде все. К семинару остались те задачи, которые были на лекции. Если кому-то непонятно. Если что-то непонятно, вы спрашиваете, разберемся.
Когда мы раздутие самое обычное делаем, мы, по сути, добавляем просто отрезок, и там все равно рационально получается.
Обычное раздутие, да. Ну, в смысле, стоят в одной точке, это добавить сумму этих самых.
Я не очень понял, а зачем мы хотим добавлять лучи?
Мы не хотим новых дивизоров. Новые дивизоры — это не то, что мы хотим. So no lecture next 2 weeks. And I'm sorry the sheet is in Russian, but if you want, I will find the English version for you. I have no time to... Так, сейчас.
Ну, и то есть раздутие под структуру не подходит, потому что не добавляем дивизор.
Ну, в смысле, раздутие подо что не подходит? Под определение разрешения особенностей оно не подходит, потому что мы добавили...
То есть раздутие это не разрешение. Ну, как в смысле не разрешение?
Ну да, это бирациональный морфизм, который как бы симпатичный, иногда нужный, но не то, что мы хотим. Да. Сейчас. Сейчас я его... Да, еще есть бонусный листочек, который тоже можно порешать. Какой хотите дедлайн?
30 июня.
Лучше май.
Ну, тут у вас как бы... Проблема в том, что если вы хотите такой дедлайн, никто вас не послушает в таком оптовом размере. Ну, давайте какой-нибудь разумный дедлайн назовем. Так. Ну, давайте месяц. Что это будет?
30 апреля.
Давайте найдем четверг. 30... Ой, елки-палки, 30 апреля.
Это четверг.
Я как раз хотела лекцию 30 апреля перенести на чуть пораньше.
Ну, можно...
Кстати, а кто готов прийти не 30 апреля, а в апреле, а чуть-чуть пораньше, 27-го, например?
Ладно.
27-го.
Или,
Во сколько?
не знаю. Ладно, я подумаю, сама голосовалку отму, не пришло. Я бы очень хотела 30 апреля куда-нибудь перенести. Ну ладно, пока напишем 29 апреля дедлайн.
У нас не будет коллоквиумов, да, никаких
Чё?
экзаменов, только в сессию. Последний, да. На коллоквиумах контрольных никаких не будет.
Нет, не будет. Просто сейчас есть четверокурсники, которым придется делать экзамен пораньше.
А можно будет его тоже пораньше сдать, если захотеть?
Ну, вообще можно, да.
Ну, просто у нас гос вот на 3-м курсе.
Сейчас, одну секунду. Я, кажется, где-то отвечала, когда я не вижу, что мне как сказала. Я вам посылаю в чат тогда, если кто-то что-то увидел, вы мне пишите сразу в личку. Сейчас. Так. Я послала. Но он не идет. Если хотите, я могу его... Нет, сейчас доползет. А по поводу экзамена, опять же, тут есть непонятность, его делать домашний или вживую.
Домашний. Очевидно.
В смысле, почему очевидно?
Ну, меньше стресса. Он двух не домашний. Я думаю, что проголосуют больше за домашний. Это моя интуиция, мне так подсказывает.
Ну ладно. Но домашний всяко сложнее будет, чем очный.
Я знаю. Ну, это не остановит некоторых людей голосовать за домашний.
Ну ладно. Вот, слушайте, он ушел даже. Он пришел?
Ну, Ваня, Жули точно проголосует за домашний.
Ваня же сказал, что не пишется сейчас.
А?
Ваня же сказал, что не пишется.
Отпишется?
Да.
Ну, понятно. Этого я не знаю.
Так. Ну что? Листок 2 и листок 2 бонусный.
А сколько задач надо сделать? 6?
Я не написала. Да, наверное, 6.
А из бонусного задачи считаем? Или только из...
За бонус вы можете получить как бы десятку, если все сдадите.
Сейчас, какая система? Как получить 10? Максимальное количество баллов как считаю. Сдать все? Или...
Смотрите. Моя схема оценивания неустойчива к людям, которые хотят просто сдать и все.
Неустойчиво?
Неустойчиво,
Конкретно?
да.
Ну, как-то
Еще раз.
нечестно. Правила игры неизвестны.
Нет, в смысле, они как бы известные. Я вам говорю, если вы сдаете из листочка, я просто забыла напечатать. Давайте я сейчас подправлю этот момент. Значит, 10 ставится за 6 задач.
Из листка 2, да?
Да,
А из листка 2,5.
все задачи. Сейчас напишу. Где? Написано, 10 ставится за задачу, всех задач. Написано уже.
Не, сейчас вот если я решил 6 задач из первого листка, то за 2,5 можно еще 10 получить?
Да, листок 2,5 можете получить еще 10, да.
А, как? Отдельный листок?
Да,
А.
вообще отдельный, да. Нет, правильно игры как раз я вам
Не,
говорю.
все, нет. Я думал, просто это как бы либо 6 оттуда, либо все
Не-не-не-не-не-не.
Я вот про это.
Нет. Просто я в листок вынуждена добавлять простые задачи, чтобы если кому-то сложно, можно было это решать и все. Но это же не означает, что все те, кому легко, должны решать только простые задачи.
Ну,
Я же говорю, неустойчиво получилось.
Мгм.
Кажется, что мы не компилировали что-то.
Наверное, запись. Запись, наверное.
Ой, да, спасибо. И надо сейчас будет сохранить этот PDF.